linked list madness. We're going to cover circular linked list, doubly linked list, pointers going everywhere. It is going to be fun. I say here, wish me luck. Let's jump right into this. As always, though, starting with review questions. What is the running time to delete the first element of a sorted array, given that we don't want to have any holes in the array, right? We can't just delete something and leave it at that. So what is the running time to delete an element of a sorted array, not leaving any holes in the array? Pause the video, come back for the incredible answer. What is it? O of n. Because even if we delete, we're going to have that hole, so we have to, worst scenario, shift over all items back if we ended up deleting, as a worst scenario, that first element in the array. What would be the best element to delete where we wouldn't have any shifting? Of course, it would be the last element in the array, but we care about big O, worst case scenario. What is the running time to delete the first element of a linked list? Doesn't matter if it's sorted or unsorted. What's the running time? Delete that first element of a linked list. Pause the video, come back. What's the answer? The answer is constant time. It's O of 1 because we're only changing 2 total connections. There's no shifting. We're changing 1 connection. When we're inserting, we're changing 2. When we're deleting from a linked list from the front, we're just taking head, and instead of head storing the address of the first node, head's going to store the address of the second node. That single line of command effectively deletes that previous first node, and the Java garbage collector, as we've said, has no mercy, and it completely removes it, saying sorry, not sorry. You've got to play with the Stream Deck. It happens in constant time. What is the running time to delete the kth element from a sorted linked list? Not the first element, but what is the running time to delete the kth element? Pause the video. Think about all of the time that is required to make that happen. Pause and come back. The answer is O of k. The deletion in and of itself happens constantly. If we have access to the predecessor of that kth item, it's an O of 1 deletion. But how do we get to that kth item? We need to traverse over k items, or really k minus 1 items, effectively k items if k is such a huge number. We have to traverse over all those items to get to the predecessor of that kth item, and then make that predecessor point directly to the successor. Doubly linked lists. Let's jump in. And the best starting point is to identify what are some of the limitations of a singly linked list. Well, insertion at the front of a singly linked list is O of 1, constant time, changing 2 addresses. Deletion from a singly linked list at the front, O of 1, super fast. But now insertion and deletion from elsewhere in the list is O of 1 because you have to traverse to find that spot where you're going to insert at, or to find that spot where you're going to be deleting from. Both insertion and deletion, they require the use of the predecessor, that previous node. And we can also only traverse in one direction. These are advantages. I'm sorry, these are not advantages. These are the disadvantages, the limitations. How can we overcome those limitations? Using a doubly linked list. Why is it called doubly linked list? Because every node has 2 references now. It has a next that points to the node that follows, and it has a previous which points to the previous node. So here is just a generic node depiction. It has a next and it has a previous, and here is a basic depiction of a doubly linked list. We have this first node, which is Tom. Tom points over, these are fantastically creative names from the publisher of this book, by the way. Tom points over to Bob, Bob points over to Harry, Harry points over to Sam. The previous of Sam points back to Harry, the previous of Harry points to Bob, the previous of Bob points back to Tom. Now Tom has no previous because Tom is the first node, and so Tom's previous would be null. Similarly, the next of Sam will be null because there is no node after Sam. Just like a linked list, but now we have a previous in addition to that next. Here is our doubly linked list node class. So instead of calling it LO node, Here I called it DLL node. The only difference on this teaching example is, and through the magic of pause, by the way, I'm going to fix something here, and we are back. Magic of pause, I made this all say DLL node. It had an underscore in there and it was mistyped. So here is our node class for a doubly linked list node. Only difference is we have a next along with, we have a previous along with that next, right? Previously we had int data and LL node next. Now we have int data, DLL node next, and DLL node previous to store the address to the previous node in our list. So we have 3 data fields. So normally we have that all that information of the actual node followed by a next, which is really the most important part to link the nodes. Well, now we have a next and a previous. Here is the doubly linked list class. Think about what may be really the only difference in this class, or the major difference. You're going to have the insert method, the delete method, and those will be changed certainly. But what's the major difference in this class? Think about what the linked list class had. It had a single variable called what? Called head. Well, now we need not only access to the head, but we need access to the end of the list, often called the tail of the list. The benefit is now insertion at either end is going to be O of 1. Insertion anywhere else is, of course, still O of n, but we can insert at the front. We can also insert at the back, at the end of the list, at the tail of the list. Here's our class. We have a head and a tail. We have our constructor. And then, of course, we have many sample methods. There's your traditional isEmpty method and many methods that follow. Here's our representation. Just like a linked list, we have a doubly linked list object that we've created, just one object. That object has a head and it has a tail. And now we're going to create nodes of the DLL node class. We have these nodes. They get connected via the insert method, right? That is part of the doubly linked list class. And of course, the tail is going to point over to that last node of the list. So what we're really going to do, I'm at 7 minutes right now. The bulk of what this video is going to cover is really just the next 2 main ideas. Inserting a new node into a doubly linked list and deleting a node from a doubly linked list. Because it's really a matter of understanding the connections, what's pointing to what, and how do we make this happen. So here we have an existing list. It starts somewhere. We don't need to worry about the head. We don't need to worry about the tail. But here in this list, we have Harry currently pointing over to Sam. And of course, Sam is pointing backwards towards Harry. Harry's pointing backwards towards someone else. That's not important. We have these 2 nodes. And we want to insert a new node between them, Sharon. Well, here's Sharon. And we want to insert Sharon between Harry and Sam. It turns out there's 4 lines of code that make this happen. And it's I want to say it's hard to think about it, but it's not hard as long as we first really identify which node needs to point to which other node and in what order does that really need to happen to make this work correctly. So let's go jump over to the tab and walk through this step by step. But even before I do that, let's think very briefly, what should happen first here? Should we first, or what would happen first? Food for thought. If we made right off the bat, if we said, let's make Sam point over to Sharon. If we said, let's make that happen first. Sam is going to point over to Sharon. Well, then how would we make Harry point to Sharon or even get to Harry? Because I would tell you, if we make Sam point over to Sharon right now and Sam no longer points back towards Harry, how do we even get to Harry? Because we only have access via help pointer, which is currently pointing to Sam. And we also have access to Sharon, this new node, via the variable called new node. But we have a help pointer traversed down our list. And on this particular example, help pointer is pointing directly to Sam. So if we make Sam point to Sharon right off the back, what's the consequence? Well, the consequence is that how do we get to Harry now? Because the only way we got to Harry was via Sam because the help pointer was pointing to Sam. So help pointer, which comes to Sam, dot previous would bring us over to Harry. Well, if we make the previous of Sam point directly to Sharon, now we've lost our access to Harry via Sam, which was via the help pointer. So the point of just mentioning that is there's really an order that these things have to happen in order to make this work correctly. Let's go jump over to the tab. And here we have that exact same picture. And what I went ahead and gave is I gave comments here showing what needs to happen first. We need to first make Sharon point to Sam, which means if I want to make Sharon point over to Sam, specifically, what of Sharon needs to point to Sam? And the answer is the next, which is right here. We need this next of Sharon to point over to Sam. And then we need Sharon to point over to Harry, which means we need the previous of Sharon to point over to Harry. Once that's done, we need Harry to point to Sharon. And so Harry pointing over to Sharon, that would be the next of Harry, pointing to Sharon. And then finally, we need to make Sam point to Sharon, which means the previous of Sam should come point over to Sharon. Those are the 4 instructions, and that's the order in which it can happen. But really, the most important part of this order is to make sure that this last thing right here of Sam pointing to Sharon, we need to make sure the previous of Sam pointing over to Sharon, that happens last. Because if that happens first, then Sam will no longer have access to Harry, and we can't therefore make Sharon point to Harry, nor can we make Harry point back to Sharon, because we won't know where Harry is via the help pointer. Because right now, remember, we only have access to any of this stuff via the help pointer. And the help pointer is pointing directly to Sam. So we can't change who Sam points to until that last step, because we don't want to lose Harry. So think about that very first instruction, which says we need to make Sharon point to Sam. We need to make Sharon point to Sam. In specific, or in particular, we want the next of Sharon to point to Sam. We want this, right? We want the next of Sharon to point to Sam. So you start from that comment and say, okay, I want Sharon to point to Sam. So I want Sharon to point to Sam. And how do we come up with the code? Well, this is what I encourage you to do. What you should do is first identify who you want to point. I want Sharon to point to Sam, and you want them pointing where? And then try to ask yourself, well, what is the address of each of those things? Or where is the address? So where is the address of Sam? The address of Sam is stored inside what? Here's Sam. Where's the address of Sam? It's stored inside help pointer. And you want that address to get saved where? You want the address of Sam, which is inside help pointer, you want it to get saved into right there, the next of Sharon. So really, you want to take the address of Sam. So I'm going to say the address of Sam. And you want to save it into Sharon dot next. That's what you want to do. Well, now let's take this to one more step. That was like step 2. And then step 3 is we actually write the line of code. Well, what is the address of Sam? It is the help pointer. And Sharon.next, well, we don't have a variable called Sharon. What we do have, though, is a variable called new node. So this would be new node. dot next. And if you were using getters and setters, this would have been new node dot set next, and then in parentheses you would have help pointer. So this is the line of code that makes Sharon point over to Sam. Let's now look at the second line of code. This second line of code, we want Sharon to point over to Harry. Well, just simply ask yourself, fine, where do we get the address of Harry? Harry's right here. Who knows where Harry is? The answer is the previous of Sam, which is right here. That previous of Sam is storing the address of Harry, which lets us get over to Harry. So the previous of Sam. Well, who knows where Sam is? The answer is help pointer. So where is the address of Harry actually stored? It's stored in Sam's previous. I'll just write it like this. Sam's previous. And then I'll even go to the next step, which is step 3. And where is Sam's, how do we get to Sam's previous? It's help pointer. Dot previous. So help pointer dot previous, that contains, right here, help pointer dot previous, this contains the address of Harry. Take the address of Harry, and we want to save it into what? Remember, we're trying to get Sharon to point over to Harry. So we want to take the address of Harry and save it where? We want to save it right here in the previous of Sharon. So we want to save the address of Harry into the previous of Sharon. So Sharon dot previous, which is therefore going to be new node dot previous. So if I had just given you this line of code, new node dot previous equals help pointer dot previous, you'd be like, what the heck? How did you get that? Well, it's a 3-step process. We want Sharon to point to Harry. Great. Step 2. Well, how do we get Harry? Where is Harry? Harry's right here. How do we find Harry? Well, Harry is via help pointer dot previous. So help pointer dot previous, that's where we store in Sam's previous, right here, which is help pointer dot previous. That's where we store Harry's address. That's the idea. And then right here, of course, Sharon, we need the previous of Sharon to point over to that. And so therefore the new node dot previous is where we store Harry's address. Let's now look at the third line. The third line says we want Harry to point over to Sharon. Well, let's now say we specifically want what of Harry to point to Sharon? We want the next of Harry to point to Sharon. So Harry dot next, and we want that next of Harry to store the address of Sharon. And I won't even put an arrow, I'll put equals. We want the address of Sharon to get saved into the next of Harry, right? Because the consequence of which is we're going to get this right here, right? Take the address of Sharon, save it into the next of Harry. Cool. So what about step 3 now, which is just, let's write the line of code. What is the address of Sharon? That's easy. It's new node. Cool. And what about Harry.next? How do we actually get this spot right here? The next of Harry. How do we get there? We do so via help pointer, because everything's via help pointer. So help pointer comes to Sam. Then Sam.previous comes over to Harry, and now we can access the dot next. So I'm going to just write that out first in code. So it's going to be help pointer dot previous dot next. That's super, super funky. It's the first time we've seen that. Take the address of Sharon, which is right here inside new node. Right? Take the address of Sharon, which is in new node, and we're going to assign it into that next variable, which is right here. How do we get there, though? How do we get to that next variable? We started at help pointer, and we said help pointer, which brings us here to Sam's node. So help pointer dot previous brings us over here to Harry. So help pointer dot previous brings us to Harry, and now we can access this next, and we can save Sharon into there, the address of Sharon, and so now the next points over to Sharon. Let's now look at the fourth line. For this fourth line, we want Sam to point to Sharon, and so we want this to happen. We want this previous of Sam to point over to Sharon. So what needs to happen? Well, we need to take the address of Sharon and we need to save that address of Sharon into the previous of Sam. We need to save it into Sam's previous. So now let's just convert that to code. So how do we get to Sam's previous? Let me erase this right here. How do we get to the previous of Sam, which is right here? We get there via help pointer. Help pointer dot previous. So help pointer dot previous equals, what is the address of Sharon? It is simply new node. So that's a more detailed explanation of what each one of these actual comment lines are doing. Now we can actually see on the slides, step by step on the slides, what the code is actually doing as well. So here, once again on the slide, we're going to make our new node with just Sharon. Here's that node. And now we need to do what? We need to make Sharon point over to Sam. And here's that line of code. Sharon points to Sam because we took the help pointer, which is Sam's address, and we saved it into new node.next. The consequence, Sharon points to Sam. Now we want to make Sharon point over to Harry. So we need to take Harry's address and save it into the previous of Sharon. So in the next line of code, certainly we're going to see new node.previous. But what is Harry's address? Well, Harry's address is saved right here. It's in the previous of Sam. Well, what is Sam? It's accessed via help pointer. So a help pointer dot previous contains the address of Harry. Take that address of Harry, save it into the previous of Sam. The third line of code, we need to make Harry point over to Sharon. We need to make Harry point to Sharon. Here's that line of code. We take Sharon's address, which is new node, right? Sharon is saved inside new node, her address. And we take Sharon's address and we save it inside the next of Harry. How do we get that? Help pointer dot previous dot next. So help pointer brings us to Sam. The previous of Sam brings us over to Harry. And then dot next is where we save Sharon's address. So now the next of Harry points over to Sharon. And then finally, we need to make Sam point to Sharon. We need to take Sharon's address, which is saved in new node, and we need to save that into the previous of Sam, making Sam point directly to Sharon. 4 lines of code to make that insertion happen. Want to challenge yourself? Make help pointer point at Harry instead of pointing at Sam, and now try to make those same lines of code once again. Now it's different, right? Because help pointer is pointing somewhere differently. But it's just important to think about, oh, you want to make Sharon point to Harry? Well, we're really taking some address, Harry's address, and we're saving it in either the next or the previous of Sharon, depending on which side Harry can be found. Now we want to remove from a doubly linked list. Thankfully, this is easier. There's only 2 lines of code here. Here, We have Bob pointing to Harry, pointing to Sharon. And we have help pointer that has traversed over and we found the node we want to delete. We didn't even bother stopping at the predecessor. There's no need to stop at the predecessor here because we can go backwards and forwards using the previous and using the next. So we actually traversed all the way down to the node we want to delete. We want to delete Harry. Well, if we want to delete Harry, that means what? Bob needs to point over to Sharon, and Sharon needs to point back directly to Bob. How do we make that happen? Here's those 2 lines of code. Let's look at each one by one. What's really happening? Help pointer dot previous dot next equals help pointer dot next. Like, what the heck? I have a crying feeling here or a confused feeling. Let's make this happen. It's not that bad. Start on the right side of the assignment. Help pointer dot next. That's an address. Whose address is that? Help pointer dot next. We'll just look. Oh, that's storing the address of Sharon. And you're like, oh, that's big brain. So help pointer dot next, that's the address of Sharon. Where do you want to save that address? We want who to point to Sharon? We want Bob to point to Sharon. So we want to take the address of Sharon and we want to save it right here in the next of Bob. Well, you're like, well, dang, how do I get to the next of Bob? No one's pointing to Bob. Well, help pointer's not pointing to Bob. We want to take the address of Sharon, which is help pointer dot next, and we want to save it right here in the next of Bob. How do we get to that next of Bob? Via help pointer. Help pointer dot previous, which is going to bring us back to Bob, dot next. And you're like, okay, that's big brain. I got that. And that's the consequence. Now Bob points directly to Sharon. What is the next line of code? Help pointer dot next dot previous equals help pointer dot previous. Let's figure that out. Help pointer dot previous, that's the address of Bob. So the address of Bob is saved right there in help pointer dot previous. And we want to take that address of Bob and we want to save Bob's address where? Remember, the goal is we want Sharon now to point back to Bob. So we want to take the address of Bob and save it into the previous of Sharon. Well, how do you get there? How do we get to this previous of Sharon? Via help pointer. Help pointer dot next brings us over to Sharon dot previous. That's that address right there. Help pointer dot next dot previous. And what are we going to put in help pointer dot next dot previous? What are we going to put there? We're going to put the address of Bob, which is, here's Bob, and what was his address? Help pointer dot previous. And those are those 2 lines of code. Practice that. Maybe have help pointer point over here to Bob, to the predecessor, and still delete Harry. Make up your own lines of code to make that happen. Practice it with help pointer pointing directly to Sharon, and try to also delete Harry when help pointer is pointing directly to Sharon. It's a good way of practicing just these interconnecting nodes and what address ultimately gets saved where to make that change happen. Circular linked lists. Oh no, yes, we're at circular linked list. It's not a big difference. We simply link the last node to the first node and the first node gets linked over to the last node. We can build singly circular linked lists that only go in one direction. We can also build circularly doubly linked lists that go in both directions, but then the last goes back to the first and the first goes back to the last. What are advantages here? Is we can continue to traverse even after passing that first node when going backwards, or when we pass that last node, we never end at null and we just wrap back around. We can visit all of the elements from any starting point. So instead of starting strictly at the end and going backwards, or strictly at the beginning and going forwards, we can start anywhere and traverse over all nodes because we never actually reach a null. We never fall off of that list. Of course, the disadvantage, you have to be careful in your code. How do you know now, if there is no null, how do you know when to stop? There are some considerations that need to be made. So here we have 4 node objects. We have our linked list class. We have a head, we have a tail, and now we have to keep a size. That's important. Previously, we only had 2 data members in the doubly linked list class, head and tail. Well, now we need a size. We need to know there's 4 nodes. Why? Because that's how you know once you've finished looping over, traversing over all of them, once you've traversed 4 times, you know to stop. Because there is no null, otherwise you won't know where to end. And guess what? That is great. And then I say here that we're done with linked lists. There's no more discussion directly of linked lists. This is the exhaustive coverage. What remains is now practicing. Practicing interview problems on linked list, practicing leak code style problems with linked list, picking up, cracking the coding, the interview, looking at those problems, which are fantastic problems they have on linked lists, and then working on a linked list project. We will not solve a large assignment on doubly or circularly linked lists, but it's important to know those nuances, know how we can have some improved running times with them, but also know the challenges that they bring with them as well. That's all I have for you, except one final demotivator. It's a great one. Winners! Because nothing says you're a loser more than owning a motivational poster about being a winner. That's not necessarily true. Don't feel bad. Don't hate it. But they're great. Despair.com. You got to go visit the website. Take care, everyone. It's been fun.